Till now, we have been discussing how to obtain a point estimate of the 95th percentile of the exposure distribution. Now we are going to talk about how to obtain confidence intervals around this point estimate. So the upper confidence limit for the 95th percentile is of a special importance, more so than the lower confidence limit. However, we are going to study how to estimate both the confidence limits. These confidence intervals are used to, first of all, express our uncertainty around the point estimate, and also, more importantly, test hypothesis. For example, we want to determine our confidence level that the similar exposure group of workers, SEG, is in compliance with an occupational exposure limit. Or we want to determine our confidence level that the true 95th percentile of the exposure distribution is within a specific AIHA exposure control category, which is the categories 1, 2, 3, or 4. So for a single shift time-weighted average exposure limit, you recall that we need to focus on the upper tail of the distribution and not one of the measures of central tendencies such as the arithmetic mean or the geometric mean. And in particular, we're going to focus on one decision statistic, i.e. the 95th percentile. The idea is we want to calculate the 95% upper confidence interval for the 95th percentile decision statistic. It is also called as the upper tolerance limit, or UTL. The 95% upper confidence limit can be used to test the hypothesis. The null hypothesis, H0, is that the 95th percentile is greater than or equal to an occupational exposure limit, whereas the alternate hypothesis is that the 95th percentile is less than the OEL. And the interpretation of such a hypothesis testing is that if the 95% UCL is less than the occupational exposure limit, then we can say that we are at least 95% confident that the true 95th percentile is less than the occupational exposure limit. And so you can see why this is of great importance when we are looking at compliance of a particular exposure scenario with an occupational exposure limit, and why it's important for risk management. So continuing on, we want to know with 95% confidence that the 95th percentile is less than a certain value. And there are K-factor tables for normal distributions, and these tables are at the back of any statistics book. However, they are also in most Excel spreadsheets, and in fact, they are in particular going to be in the spreadsheet that I'm going to discuss a little bit later, which is part of your toolkit. So these K-factor tables provide these K-factors, which are a function of several parameters, gamma and phi, and I'll describe what they are in a second. And these are such that the probability is gamma that at least a fraction phi of the distribution is less than the arithmetic mean of the log transformed values, mu sub y plus factor k times sigma y for a given sample size of n. So mu y and sigma y are the mean and standard deviation of the log transformed values of the exposure that are now normally distributed. So the upper confidence limit can be expressed in this equation, the mu g, which is the geometric mean, times sigma g, which is the geometric standard deviation, raised to the power this k factor. In order to estimate the 95% upper confidence limit, as we have done in the past, we first calculate the geometric mean and the geometric standard deviation. And then using our sample size n, we read the upper confidence limit k value from the appropriate table. And I'll show that table in my next slide. So let's assume that we are interested in a 95% confidence level, so that the value for gamma is 0.95. And then our percentile, our proportion P is the 95th percentile, so P is 0.95, and N is our sample size. And so using the geometric mean, geometric standard deviation, and K that we calculated in the previous step, we can calculate the 95% UCL as follows. So the 95% UCL is given as the exponent of the arithmetic mean of the log transformed values, which is the y bar, and then you have the standard deviation of the log transformed values, which is the S sub y, which is multiplied by the K factor. So in this slide, what I'm showing is a table of K values. At the very top, you will see the parameter gamma, which is the confidence level we desire, which is the 95% confidence level. And along the top, in the second row, you see the p-values. So these are the different percentiles that we may wish to estimate. And so we are interested in the 95th percentile. So we move over to the 0.95 column. If, for example, we were interested in the 90th or the 99th or the 99.9th percentile, you can look at those additional columns. On the rows, you see our sample size. So the sample sizes start from 3, 4, 5, and so on. And for our particular data set that we have encountered before, we have a sample size of 6. And we are interested in the 95th percentile, and we are interested in the 95% upper confidence limit. So we look at the intersection of n equal to 6 sample size and the 95th percentile column, and we get a K value of 3.707. So now if we want to calculate the 95% UCL, we have already calculated the arithmetic mean of the log transformed values of our 6 data points. So this is the y bar that we have previously calculated. And we also calculated the standard deviation of the log transformed values, sy. So we plug these values into our formula, and our K value that we just determined is 3.707. So our 95% upper confidence limit is the exponent of y bar, which is 0.0620, the K value, which is 3.707, and the sy, which is 0.6043. And we get a value of 10 milligrams per cubic meter for our data set. It is worth reflecting on this calculation and going back to the K value table and think about different alternative calculations we might have done. So let me go back to the previous slide for just a minute. And let's say we had, instead of 6 data points, we had only 3 data points. And so now our n value that you can read from this table is 7.655 for a 95% confidence limit. So now we have a much larger K. And if you now go back to this particular slide, you can see that our upper confidence limit is going to be much greater than if we had 6 data points. And this reflects our uncertainty. So the fewer the number of data points we have, the greater is the uncertainty in our estimate of the 95th percentile. So the 95% UCL is going to be much larger. Again, let me go back to this table again. So as our sample size increases, you can see that the K value is decreasing. And so we'll have tighter and tighter uncertainty interval around our point estimate. If you also look at other columns, so let's say we were interested in the 99th percentile. Again, if we just had the same number of data points, n equal to 6, again, our K value increases. So our uncertainty with just 6 data points is much greater for estimating the 99th percentile than for the 95th percentile or even the 90th or 75th percentile. So there are these sorts of things we can observe when we consider the K table. One interesting thing that is worth noticing is if you were to carry on further down the table as n increases for the 95th percentile, you can see that it's decreasing, but the table is not complete. So you might say, well, what is the value of k when n is very large, approaching infinity. Our instinct is to say, well, it's going to go down to 0, but that is in fact wrong. As our sample size increases indefinitely, this is a table that is going to estimate the upper confidence limit. And it's going to narrow down into our point estimate of the 95th percentile. So as our n increases, the k value will go down to 1.645, which you recall is the value used for calculating the point estimate of the 95th percentile. So as n increases indefinitely, the point estimate becomes the upper tolerance limit also. Let's come back to this calculation. We had said that the 95% upper confidence limit for our data set is 10 milligrams per cubic meter. If you go back to the log normal distribution for this data set, you will recall that we had calculated a geometric mean of 1.06 milligrams per cubic meter. That's near the peak of this distribution, or the mode. We had calculated a geometric standard deviation of 1.83. And using these two, we had calculated the 95th percentile as 2.8. And that is shown by the vertical bar at that point. Now we have also calculated the upper confidence limit of the 95th percentile, and that is 10. That is a whole order of magnitude greater than the geometric mean. So the implication for this is that even though the geometric mean, which is a measure of the central tendency of this distribution, is around 1, we are really interested in the upper confidence limit of the 95th percentile, and we are going to compare that value to an occupational exposure limit. And that is a whole order of magnitude greater. Another thing to consider is that if you were to make a small set of measurements, in this case we made 6 measurements, all of them are less than the 95th percentile. They are all in the middle, under the big hump of the distribution. And so we use a small number of measurements at the lower end of the exposure distribution to make very important inferences about the upper tail of the distribution, which we typically never observe.